Hey, sleepers. Welcome to Sleepy Lectures, the show where bedtime meets the cosmos and staying awake is strictly optional. Tonight, we're floating in a quiet, dark expanse. The silence is perfect. Below you, a gentle blue and white marble spins slowly. It's home. But tonight, we're looking away from home. We are looking out into the grand, peaceful darkness that surrounds it. We see a brilliant, warm light in the distance. And closer to us, we see other points of light. Some are steady. Some are reddish. Some are a brilliant silver. These are our neighbors. This is our celestial family. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you feel so inclined, I would love for you to share your location and local time in the comments. It's a wonderful way for us all to feel connected, scattered though we are across our spinning world, all listening together under the same vast sky. So close your eyes, take a deep breath, and get ready to drift off as we explore the fascinating facts behind our solar system and more. Let us begin our journey at the very heart of our neighborhood, the center of everything, the reason we are all here. Let's drift toward the sun. The sun is a star. It seems obvious, but it's a profound truth. The same kind of object as the countless glittering specks you see in the deepest night sky. The only difference is that we are incredibly close to this one. It is our star. Imagine a campfire, a truly colossal campfire, so big that you could fit 1 million Earths inside of it. This campfire isn't burning wood. It's burning something much more fundamental. It's burning itself. The sun is a gigantic ball of hot gas, mostly hydrogen and helium, the two simplest and most abundant elements in the entire universe. And deep within its core, the pressure is immense. The temperature is staggering. It is so hot and so squeezed together that something truly magical happens. A process called nuclear fusion. Now, that term might sound a little complicated, but we can think of it in a very simple way. Imagine you have a huge pile of tiny, lightweight building blocks. These are the hydrogen atoms. The gravity of the sun is like a giant, invisible hand squeezing this pile with unbelievable force. It squeezes so hard that 4 of these little hydrogen blocks are forced to merge. They fuse together, and when they do, they become one slightly larger, slightly different block, a helium block. But here's the wonderful part. When those 4 hydrogen blocks become one helium block, a tiny bit of their mass is left over. It doesn't just disappear. It is converted into a pure burst of energy, light and heat. This process happens trillions and trillions of times every single second inside the sun's core. It is a continuous self-sustaining explosion that has been burning for 4.5 billion years. And it will continue to burn for about another 5 billion years. It is steady. It is reliable. It is the engine of our solar system. Finally, you reach the surface, the photosphere. And from there, your journey is swift. You fly out into the blackness of space at the fastest speed possible, the speed of light. It takes you just 8 minutes and 20 seconds to travel the 93 million miles to Earth. Feel that journey now, that final swift flight. And then you arrive. You land gently on a leaf, helping a plant grow. You warm the face of a sleeping person. You splash into the ocean, warming the surface of the water. Every ray of sunshine that has ever touched your skin has completed that same epic journey. 100,000-year dance inside the sun, followed by an 8-minute sprint across space, all to deliver a little bit of warmth to you. But what it was actually made of remained a mystery. For a long time, scientists thought the sun was made of the same elements as Earth. Perhaps it was a giant ball of burning coal. But that didn't add up. It would have burned out long ago. It wasn't until the 1920s that a brilliant young astronomer named Cecilia Payne-Gaposchkin made a revolutionary discovery. She was studying the light from the sun and other stars. She analyzed their spectra. You can think of a spectrum as a rainbow of light, but with tiny dark lines in it. These lines are like fingerprints. They tell you exactly what elements are present in the star. Her calculations showed something that went against all the scientific beliefs of her time. She found that the sun was made almost entirely of hydrogen and helium, not iron or carbon or oxygen, like the Earth. Her conclusion was so radical that the senior astronomers of her day told her she must be wrong. They advised her to change her conclusion in her doctoral thesis. She did, reluctantly, adding a note that her result was almost certainly not real. But a few years later, those same astronomers, using their own methods, proved that she had been right all along. Cecilia Payne had discovered the true composition of the universe. She had shown that stars are fundamentally different from planets. It was one of the most important discoveries in the history of astronomy, and for a long time, she received very little credit for it. Today, we remember her as a true pioneer, a woman who looked at the sun and saw the truth when others could not. The sun is not just a source of light and heat. It is also the gravitational anchor of our solar system. Its immense mass, its sheer heaviness, creates a powerful gravitational field. It is like a deep well in the fabric of space-time. The planets, asteroids, and comets are all rolling along the edge of this well. They are constantly falling toward the sun, but they are also moving sideways very, very fast. Imagine you tie a ball to a string and swing it around your head. The string is constantly pulling the ball toward your hand. That's gravity. The ball's forward motion is what keeps the string taut and stops the ball from just flying into your face. That's orbital mechanics in a nutshell. Each planet is a ball on a string, and the sun is the hand holding them all. The sun also has a powerful influence that extends far beyond gravity. It constantly breathes out a stream of charged particles. This is called the solar wind. It flows outward from the sun in all directions, traveling at hundreds of miles per second. This wind sweeps through the entire solar system. Most of the time, we are protected from this solar wind by Earth's magnetic field. Our planet has a molten iron core, which acts like a giant bar magnet. This creates an invisible shield around us, the magnetosphere. The solar wind flows around this shield, like water flowing around a rock in a stream. But sometimes, some of these particles get trapped. They are funneled down toward the Earth's poles. When they hit the atoms in our upper atmosphere, they make them glow. This is what creates the beautiful, shimmering curtains of light we call the aurora borealis in the north and the aurora australis in the south. So, when you see those dancing green and purple lights in the sky, you are witnessing a direct interaction between our planet and the sun. A cosmic light show powered by our star. The sun is not perfectly calm. It has moods. It has cycles. It goes through periods of high activity and low activity, roughly every 11 years. During its active periods, its surface is freckled with sunspots. These are cooler, darker areas on the sun's surface, caused by intense magnetic fields. Sometimes, these magnetic fields get twisted up and snap like a rubber band stretched too far. This can release a tremendous burst of energy, a solar flare, or a coronal mass ejection, which is an enormous bubble of gas and magnetic fields hurled out into space. These events can be powerful, but we don't need to worry. Our atmosphere and magnetic field are excellent protectors. These solar storms are a reminder that our star is a dynamic, living thing. It is not just a static ball of light in the sky. It is an active, complex, and fascinating star. Our star. So let's leave the heart of our system now. Let's drift away from the sun's immense warmth and light and begin our tour of the planets that call it home. We will travel outwards, starting with the ones huddled closest to the fire. The first planet we encounter is Mercury, the smallest of the 8 planets and the closest to the Sun. Mercury is a world of extremes. It is named after the Roman messenger god, who was known for his speed, and the name fits. Mercury zips around the Sun faster than any other planet, completing a full orbit in just 88 Earth days. A year on Mercury is less than 3 months long. But its days are a very different story. Mercury spins on its axis very, very slowly. So slowly that one day on Mercury, from one sunrise to the next, lasts for 176 Earth days. That's 2 of its years. Imagine a day that is twice as long as a year. It's a strange and wonderful concept. Because it is so close to the sun and has almost no atmosphere to trap heat, its temperatures are wild. During its long day, the surface can reach over 800 degrees Fahrenheit or 430 degrees Celsius, hot enough to melt lead. But during its equally long night, with no blanket of air to keep it warm, the temperature plummets to minus 290 degrees Fahrenheit or minus 180 degrees Celsius. Mercury looks a lot like our own moon. It is a pockmarked, cratered world. It has been battered by asteroids and comets for billions of years. Its surface is a testament to the chaotic early history of our solar system. You can think of it as a historical document, written in the language of craters. For a long time, we thought Mercury was just a simple, geologically dead rock. But recent missions, like NASA's Messenger spacecraft, have shown us that it is more complex. It has a surprisingly large iron core, which makes up about 85% of the planet's radius. It's like a giant iron ball bearing with a thin, rocky crust. This large core also gives Mercury a weak magnetic field, something we didn't expect to find on such a small, slowly rotating planet. And here is perhaps the most surprising thing about Mercury. At its poles, in the bottoms of craters that are permanently shielded from the sun's blistering rays, scientists have found evidence of water ice. Ice on the planet closest to the sun. It's a beautiful paradox. These craters are some of the coldest places in the entire solar system, existing just a few hundred miles from a surface hot enough to melt metal. It shows us that even in the most extreme environments, you can find pockets of the unexpected. Let's continue our journey outwards. The next stop is a world that is often called Earth's twin. But if it is our twin, it is our evil twin. This is Venus. Venus is the second planet from the Sun. It is almost the exact same size as Earth. It has a similar mass. It's made of similar rocky materials. For a long time, astronomers imagined it might be a lush, tropical paradise hidden beneath its thick, perpetual cloud cover. A world of swamps and jungles. Science fiction writers love to set stories there. They could not have been more wrong. Venus is the hottest planet in the solar system, even hotter than Mercury, though it is farther from the Sun. Its surface temperature is a constant, uniform 900 degrees Fahrenheit or 475 degrees Celsius. It is hot enough to melt lead and zinc, and this heat is everywhere. It is just as hot at the poles as it is at the equator. It is just as hot at night as it is during the day. Why is it so hot? The answer lies in its atmosphere. Venus has an incredibly thick, dense atmosphere, about 90 times thicker than Earth's. The pressure on the surface is equivalent to being 3,000 feet, or nearly a kilometer, deep in our ocean. It would crush a submarine. And this atmosphere is made almost entirely of carbon dioxide. This is a powerful greenhouse gas. The sunlight that manages to get through the clouds heats the surface. The surface then tries to radiate that heat back out into space. But the thick blanket of carbon dioxide traps the heat. It can't escape. This is called a runaway greenhouse effect. Venus is a cautionary tale of what can happen when the greenhouse effect goes completely out of control. Its clouds are not made of water, like ours. They are made of droplets of sulfuric acid. It rains acid on Venus, but it is so hot that the acid rain evaporates long before it ever reaches the ground. Landing on Venus is one of the greatest challenges in space exploration. The Soviet Union was particularly fascinated with Venus and sent a series of probes called the Venera missions. These were tough, heavily armored landers. Venera 7 was the first spacecraft to successfully land on another planet. In 1970, it survived for just 23 minutes before succumbing to the heat and pressure. Later missions lasted a little longer, some for up to 2 hours. They sent back the only images we have from the surface of Venus. They show a bleak, orange-lit, rocky landscape, a truly alien world. Venus also spins backwards. Compared to most other planets, it rotates in the opposite direction, and it does so incredibly slowly. One day on Venus is 243 Earth days long. This is longer than its year, which is 225 Earth days. So on Venus, a day is longer than a year. It's another planet with a very strange sense of time. So Venus is not a welcoming place. It is a blistering, crushing, toxic world, but it is still a fascinating one. It teaches us about the delicate balance that allows a planet like Earth to be habitable. It reminds us that being the right size and in the right general location is not enough. A planet's atmosphere is the key to its climate, and Venus shows us what happens when that climate goes terribly, terribly wrong. Leaving the inferno of Venus behind, we drift a little further from the sun, and we come to a familiar place. A beautiful blue marble, swirled with white clouds. A world teeming with life. We come home. This is Earth, the third planet from the Sun, and as far as we know, the only place in the entire universe that harbors life. It is in what astronomers call the habitable zone, or the Goldilocks zone. Not too hot, not too cold. It's just right. The most important ingredient for life, as we know, it is liquid water. And Earth is covered in it. About 71% of our planet's surface is ocean. This massive amount of water helps to regulate our climate, absorbing heat and releasing it slowly. It is the cradle of life. Our atmosphere is another key ingredient. It's a thin, delicate layer. If the Earth were the size of an apple, the atmosphere would be no thicker than the skin of the apple. But it is vital. It is mostly nitrogen and oxygen. It gives us air to breathe. It protects us from the sun's harmful ultraviolet radiation. It burns up most of the small meteors that head our way, creating shooting stars. And it provides a modest, stable greenhouse effect that keeps our planet at a comfortable average temperature. Unlike Venus, our greenhouse effect is a good thing. It keeps us from freezing. We also have a strong magnetic field, as we mentioned earlier. This shield protects our atmosphere from being stripped away by the solar wind. Mars, as we will see, was not so lucky. And we have a large moon. Our moon. Its gravitational pull stabilizes the Earth's wobble. It prevents our planet from tilting too erratically, which would cause wild and extreme climate shifts. The moon also gives us the tides, the rhythmic rise and fall of the oceans. Some scientists believe that these tides, in the early history of Earth, may have been crucial for creating the primordial soup in shallow pools where life could begin. Our planet is also geologically active. We have plate tectonics. The Earth's crust is broken up into giant plates that are constantly shifting and moving. This process recycles elements. It creates mountains and oceans. It drives volcanic activity, which releases gases that replenish our atmosphere. A geologically active planet is a living planet. For a moment, let's just pause here. In our journey across the solar system, let's just float above our home. Visualize the deep blue of the oceans, the rich green and brown of the continents, the wispy, brilliant white of the clouds. See the lights of the cities twinkling on the night side of the planet. There is a sense of peace, a sense of fragility, and a sense of immense beauty. This is our spaceship, our shared home, drifting in the vast, quiet emptiness of space. It is a precious and unique place, the result of a long chain of fortunate coincidences. The right distance from the right kind of star, the right size, the right atmosphere, the presence of water, a large moon, a magnetic field, plate tectonics. All of these things came together to create the one world we know that is bursting with life. Now, let's reluctantly leave our beautiful home and continue our journey outward. Our next destination is one of humanity's greatest fascinations, the red planet, Mars. Mars is the fourth planet from the Sun. It's about half the size of Earth. It is a cold, dusty desert world. Its reddish color comes from iron oxide, rust. The surface of Mars is literally rusty. It has a very thin atmosphere, less than 1% as thick as Earth's. It's mostly carbon dioxide, like Venus, but there's just not enough of it to create a significant greenhouse effect. So Mars is very cold. The average temperature is around minus 80 degrees Fahrenheit, or minus 60 degrees Celsius. But Mars was not always this way. We have overwhelming evidence that in the distant past, billions of years ago, Mars was a warmer, wetter world. It had a thicker atmosphere. It had liquid water flowing on its surface. We can see the evidence written all over its face. There are dried up riverbeds. There are vast deltas where rivers once flowed into ancient craters. There are minerals on the surface that could only have formed in the presence of water. So what happened? The leading theory is that Mars lost its magnetic field. Because it's smaller than Earth, its core cooled down and solidified faster. The protective magnetic shield vanished. And over millions of years, the solar wind stripped away most of its atmosphere. The air grew thin, the pressure dropped, and the liquid water either boiled away into space or froze into ice, which is now locked up in its polar ice caps and buried underground. This story of a once habitable world that lost its life-giving properties is what makes Mars so compelling. Did life ever get started there? Could there still be simple microbial life clinging to existence in underground pockets of water, shielded from the harsh surface radiation? These are the questions that drive our exploration of Mars. We have sent a small army of robotic explorers to find the answers. Orbiters that map the planet from above, landers that study the weather, and rovers, our intrepid little robotic geologists on wheels. Rovers like Spirit and Opportunity, which were designed to last for 90 days and ended up exploring for years. Opportunity roamed the Martian surface for nearly 15 years, a remarkable feat of engineering. And today, we have the Curiosity rover, exploring a crater that was once a lake, and the Perseverance rover, which is actively searching for signs of ancient life. Perseverance even has a little helicopter companion named Ingenuity, the first aircraft to fly on another planet. These rovers are our eyes and our hands on Mars. They are an extension of our own human curiosity, and they are painting a picture of a world that is fascinatingly complex. Mars has the largest volcano in the solar system, Olympus Mons. It's a shield volcano 3 times the height of Mount Everest. It has a vast canyon system, Valles Marineris, that would stretch all the way across the United States. It has 2 tiny, lumpy moons, Phobos and Deimos. They are likely captured asteroids. Mars is the most Earth-like planet in our solar system, besides Earth itself. It has seasons, just like we do, because its axis is tilted at a similar angle. A day on Mars, called a sol, is only about 40 minutes longer than an Earth day. It has polar ice caps that grow and shrink with the seasons. It is the next frontier for human exploration. The dream of sending astronauts to walk on the red soil of Mars is a powerful one. It would be a monumental step for humanity. A journey to a world that may have once been a second cradle of life in our solar system. Our tour of the inner, rocky planets is now complete. We have seen a scorched, cratered world, a hellish, pressure cooker world, a perfect, living world, and a cold, rusty, fossil world. They are all so different, yet they all formed from the same cloud of dust and gas around the same star. Their stories show us the diverse paths that a planet can take. Now, we must cross a great divide. Between the inner rocky planets and the outer gas giants, there is a vast, empty space. But it is not entirely empty. This is the realm of the asteroid belt. When the solar system was forming, planets grew by sweeping up smaller bodies called planetesimals. In most regions, these planetesimals accreted to form the planets we see today. But in the region between Mars and Jupiter, something different happened. The immense gravitational influence of Jupiter, the next planet out, was just too strong. It stirred things up. It pulled and pushed on the planetesimals in this region. It was like a giant cosmic blender. It prevented them from ever clumping together to form a single large planet. So instead of a 5th rocky planet, we have the asteroid belt, a vast, donut-shaped ring of millions of rocky and metallic objects, all orbiting the sun. Now, when you see the asteroid belt in movies, it's often depicted as a dense, crowded field of tumbling rocks that you have to dodge and weave through. The reality is quite different. Space is big, really big. The asteroid belt is enormous. The asteroids within it are, on average, hundreds of thousands of miles apart. If you were standing on one asteroid, you would likely not even be able to see the next closest one. It would just be a faint point of light, if you could see it at all. Spacecraft like the Voyager and Pioneer probes have flown through the asteroid belt without any trouble at all. The chances of accidentally hitting an asteroid are incredibly small. So you can think of the asteroid belt not as a crowded field, but as the leftover building materials of the solar system. The crumbs from the table after the planetary feast was over. The asteroids themselves come in all shapes and sizes, from tiny pebbles to giant boulders. The largest object in the asteroid belt is Ceres. It's about 590 miles, or 950 kilometers, in diameter. It's so big that its own gravity has pulled it into a nearly spherical shape. This is one of the main criteria for being a planet. But because it hasn't cleared its neighborhood of other objects, it is classified as a dwarf planet. The first dwarf planet we have encountered on our journey. Ceres was the very first asteroid ever discovered, back in 1801 by an Italian astronomer named Giuseppe Piazzi. He was looking for a missing planet that many astronomers believed should exist between Mars and Jupiter, based on a mathematical pattern. When he found Ceres, he thought he had found it. But soon, other, smaller objects were found in the same region, and the new category of asteroid was born. NASA's Dawn spacecraft visited Ceres recently and gave us a stunningly detailed look at this little world. It is a dark, cratered object, but it has some incredibly bright, mysterious spots on its surface. These spots are located inside craters, and they are so bright they shine like beacons. The Dawn mission found that these spots are deposits of salt, specifically sodium carbonate. It's thought that an ancient subsurface ocean or pockets of briny water have oozed up to the surface and evaporated, leaving the bright salt deposits behind. This suggests that even on this small, cold dwarf planet in the asteroid belt, there might be liquid water hidden beneath the surface. Water, the key ingredient for life, seems to pop up in the most surprising places. Other large asteroids in the belt include Vesta, which is lumpy and has a giant mountain at its south pole, and Pallas and Hygiea. The Dawn spacecraft also visited Vesta before it went to Ceres. It taught us that these are not just inert rocks. They are complex little worlds with their own unique histories. The asteroids are also time capsules. They have been largely unchanged since the early days of the solar system, 4.6 billion years ago. By studying them, and by studying the meteorites that sometimes fall to Earth, we can learn about the conditions and the ingredients that were present when the planets were first forming. They are a direct link to our own origins. So let's drift peacefully through this vast, sparse belt of ancient rocks. It is a quiet, contemplative space, a bridge between two very different parts of our solar system. On one side, the small, warm, rocky worlds. On the other side, the giants. And that is where we are headed next. As we cross the asteroid belt and move further from the sun, the solar system changes dramatically. We are now entering the realm of the giants, the gas giants, and the first one we meet is the undisputed king of them all, Jupiter. Jupiter is the fifth planet from the sun, and it is enormous. It is more than twice as massive as all the other planets in the solar system combined. You could fit 1,300 Earths inside of it. It is a truly colossal world. Unlike the inner planets, Jupiter is not a solid, rocky body. It is a gas giant. It is made mostly of hydrogen and helium, the same elements that make up the sun. In fact, if Jupiter had been about 80 times more massive, it would have become a star itself. It would have been a second sun in our solar system. Our solar system would be a binary star system. life on Earth would be very, very different, if it could exist at all. Jupiter has no solid surface to stand on. If you were to try and land on Jupiter, you would just descend through its thick atmosphere. The pressure and temperature would increase as you went deeper, until you were eventually crushed and vaporized. It is a world of gas that gets denser and denser until it becomes a strange, exotic liquid. Deep inside, scientists believe there is a core of rock and ice, perhaps about the size of Earth, but we can't be sure. What we can see of Jupiter is its incredible atmosphere. It is a swirling, turbulent place of colorful clouds. We see bands of white, yellow, orange, and brown. These are called zones and belts. The lighter colored zones are areas of rising gas. The darker belts are areas of falling gas. They are whipped around the planet by incredibly fast winds, some blowing at more than 300 miles per hour. The most famous feature in Jupiter's atmosphere is the Great Red Spot. This is a gigantic, swirling storm, a hurricane. It is so big that you could fit 2 or 3 Earths inside of it, and it has been raging for at least 350 years, ever since we first observed it with telescopes. It has been shrinking in recent decades, and we don't know why. It's a mystery that astronomers are eagerly watching. But even a shrinking Great Red Spot is a storm of unimaginable size and power. Jupiter is like the big brother or the bodyguard of the solar system. Its immense gravity acts like a giant cosmic vacuum cleaner. It sweeps up or flings away many of the comets and asteroids that come into the inner solar system from the outer reaches. Without Jupiter, the Earth would be pummeled by impacts much more frequently. The presence of this giant planet far out in the solar system may have been crucial for allowing life on Earth to develop in relative peace. But perhaps the most fascinating thing about Jupiter is not the planet itself, but its family of moons. Jupiter has at least 79 moons that we know of. It is like a mini solar system all on its own. 4 of these moons are particularly large and famous. They are called the Galilean moons because they were discovered by Galileo Galilei in 1610. When Galileo pointed his new telescope at Jupiter, he saw 4 tiny points of light orbiting the giant planet. This was a revolutionary discovery. It proved that not everything in the universe orbited the Earth. This was a major blow to the geocentric model of the universe and a huge piece of evidence for the sun-centered model of Copernicus. Let's visit these 4 moons. They are each a unique and fascinating world. The innermost Galilean moon is Io, is the most volcanically active body in the entire solar system. Its surface is a chaotic landscape of yellow, orange, and red, colored by sulfur compounds. It is constantly being squeezed and stretched by Jupiter's immense gravity on one side, and the pull of the other moons on the other side. This constant gravitational tug-of-war generates a tremendous amount of heat in Io's interior. This heat powers its hundreds of active volcanoes, which spew plumes of sulfur and sulfur dioxide hundreds of miles into space. Io is a world in constant violent turmoil. Next out is Europa. Europa is one of the most exciting places in the solar system in the search for life beyond Earth. It is a smooth, icy world crisscrossed with long, dark cracks and streaks. It looks like a giant, cracked eggshell. Scientists believe that beneath this shell of ice, which might be several miles thick, there is a vast, global ocean of liquid salt water. An ocean that could contain more than twice the amount of water in all of Earth's oceans combined. Like Io, Europa is also heated by the gravitational tug-of-war with Jupiter. This could provide enough heat to keep the subsurface ocean liquid. And on the floor of this dark, hidden ocean, there could be hydrothermal vents, just like the ones we find on Earth's ocean floors. On Earth, these vents are teeming with life that doesn't rely on sunlight. Could there be life in Europa's ocean? We don't know. But it is one of the most compelling questions in all of science. Future missions are being designed to land on Europa, melt or drill through the ice, and send a submarine to explore this alien sea. Let's take a moment for a visualization. Imagine you are floating in that dark ocean, deep beneath Europa's ice. The only light comes from the glow of hydrothermal vents on the ocean floor. The water is cold, but the vents are warm. The silence is absolute. It is a place of profound mystery and potential. A hidden world, locked away beneath a shell of ice, orbiting a giant planet, far from the sun. It is a powerful reminder that life might exist in places we would never expect. The next moon out is Ganymede. Ganymede is the largest moon in the entire solar system. It is bigger than the planet Mercury. It is so big that it even has its own magnetic field, the only moon to do so. Ganymede is a world of contrasts. It has old, dark, heavily cratered regions, and younger, lighter, grooved terrain. It's thought that it might also have a subsurface ocean, sandwiched between layers of ice. And finally, there is Callisto. Callisto is the outermost of the Galilean moons. Its surface is the oldest and most heavily cratered in the solar system. It is a dark, icy world that has been geologically quiet for billions of years. It is a relic from the early days of the solar system, a preserved record of the intense bombardment that all the planets and moons once endured. These four moons, Io, Europa, Ganymede, and Callisto, show us that moons are not just boring, dead rocks. They can be active, dynamic worlds, just as complex and interesting as the planets themselves. Let's leave the grand kingdom of Jupiter and continue our journey outward. Our next stop is perhaps the most beautiful and iconic planet in our entire solar system. The jewel of the night sky, Saturn. Saturn is the sixth planet from the Sun. It is the second largest planet after Jupiter. Like Jupiter, it is a gas giant, made mostly of hydrogen and helium. It also has a stormy, banded atmosphere and incredibly fast winds. But what makes Saturn so breathtaking, so universally recognized, is its magnificent system of rings. From Earth, even with a small telescope, you can see them. A stunning, delicate, and impossibly thin ring system encircling the planet. It is one of the most beautiful sights in all of nature. What are these rings made of? They are not solid. They are made of countless small particles of ice and rock. Most of the particles are tiny, the size of dust grains or pebbles. Some are as big as a car or a house. They are all orbiting Saturn together, like a vast, flat, spinning disk. The rings are incredibly wide, stretching out for tens of thousands of miles, but they are shockingly thin. In most places, they are only about 30 feet, or 10 meters thick. If you made a scale model of Saturn's rings that was a mile wide, it would be thinner than a sheet of paper. Where did the rings come from? We're not entirely sure. There are two main theories. One is that they are the remains of a moon, or perhaps several moons that got too close to Saturn and were torn apart by its powerful gravity. Another theory is that they are leftover material from the formation of the solar system that never managed to coalesce into a moon. NASA's Cassini spacecraft spent 13 years orbiting Saturn, from 2004 to 2017. It gave us our most detailed look ever at this incredible system. The lead scientist for the imaging team on that mission was a woman named Carolyn Porco. Her work and her leadership were instrumental in the stunning images and discoveries that Cassini made. She helped us see the rings not as static objects, but as a dynamic, ever-changing system. Cassini showed us that the rings are not just one solid band. They are made up of thousands of individual ringlets, separated by gaps. Some of these gaps are cleared by the gravity of small shepherd moons that orbit within or near the rings. These tiny moons act like gravitational snowplows, keeping the ring particles in line. The rings are a busy, active place. There are waves and ripples that travel through them, caused by the gravity of the larger moons. There are strange, spoke-like features that appear and disappear. There are even places where the rings are twisted and warped. It's a complex and beautiful cosmic dance. But like Jupiter, Saturn's wonders don't end with the planet and its rings. It also has a huge and diverse family of moons, over 80 of them, and 2 of them are particularly special. First, there is Titan. Titan is Saturn's largest moon. It's the second largest moon in the solar system, after Ganymede, and it is unique. It is the only moon in our solar system with a thick, substantial atmosphere. Its atmosphere is even thicker than Earth's. It's mostly nitrogen, like ours, but it's filled with a thick orange smog of organic molecules called hydrocarbons. The Cassini mission sent a probe called Hygenes down through Titan's atmosphere to land on its surface. It was the most distant landing ever made by a human-made object. The images it sent back were astonishing. They showed a landscape that looked eerily familiar. There were hills and valleys. There were river channels. There were shorelines. But on Titan, it is far too cold for liquid water. The temperature is around minus 290 degrees Fahrenheit, or minus 180 Celsius. At that temperature, water is as hard as rock. The liquid that carves the river channels and fills the lakes and seas on Titan is not water. It is liquid methane and ethane, the same stuff as natural gas on Earth. Titan has a full hydrological cycle, just like Earth, but with methane instead of water. It rains liquid methane from the clouds. The methane forms rivers that flow into vast lakes and seas. Then it evaporates back into the atmosphere to form clouds again. It is a strange, cold, parallel version of Earth, a world with liquid on its surface, a thick atmosphere, and complex organic chemistry. It's another place where scientists wonder if some form of life, very different from our own, could possibly exist. The other truly remarkable moon of Saturn is a small one called Enceladus. Enceladus is a tiny, bright white, icy moon. For a long time, we thought it was just a frozen, dead snowball. But Cassini discovered something amazing. At its south pole, there are giant fissures in the ice, nicknamed tiger stripes. And erupting from these fissures are colossal plumes, or geysers, of water ice and vapor, shooting hundreds of miles out into space. This was a stunning discovery. It means that this tiny, frozen moon has a liquid water ocean beneath its icy shell, just like Europa, and it is actively erupting that ocean out into space. The Cassini spacecraft even flew through these plumes and sampled them. It found water, salt, silica, and complex organic molecules. These are all the key ingredients for life as we know it. So Enceladus, a tiny moon of Saturn that we barely knew anything about a few decades ago, has now become one of the top places to search for extraterrestrial life. Its subsurface ocean, warmed by tidal forces, and its geysers providing a convenient way to sample that ocean, make it an incredibly compelling target for future exploration. So Saturn, the ringed planet, has given us not one, but two moons with incredible potential for astrobiology. The cold, methane-rich world of Titan, and the small, icy moon with a hidden ocean, Enceladus. Our journey is taking us further and further from the sun. The light is getting dimmer. The temperatures are dropping. We are entering the deep freeze of the outer solar system. We have left the gas giants behind. Now we come to the ice giants. The first ice giant we encounter is the seventh planet from the Sun, Uranus. Uranus is a strange and mysterious world. It is about 4 times the diameter of Earth. It is made mostly of water, methane, and ammonia ices, surrounding a small rocky core. The methane in its upper atmosphere is what gives it its pale, blue-green, cyan color. It absorbs red light and reflects blue and green light. Uranus is a very cold place. It has the coldest atmosphere of any planet in the solar system, with temperatures dropping as low as -371 degrees Fahrenheit or -224 Celsius. But the most bizarre thing about Uranus is its tilt. Most planets spin like a top as they orbit the Sun, with their axis of rotation pointing more or less up and down relative to their orbit. Earth is tilted at about 23.5 degrees. This is what gives us our seasons. Uranus is tilted at an incredible 98 degrees. It is literally orbiting the Sun on its side. Imagine a spinning top that has been knocked over, but it keeps on spinning. That's Uranus. We think that early in its history, it was struck by a massive Earth-sized object that knocked it onto its side. This extreme tilt leads to the most extreme seasons in the solar system. For a quarter of its long 84-year orbit, one pole is pointed directly at the Sun, while the other is in total darkness. Then, for the next quarter of its orbit, the equator faces the Sun. Then the other pole gets its 21-year-long summer. It is a world of very, very long days and nights. Uranus also has a faint system of dark rings, much darker and thinner than Saturn's. And it has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. Moons like Miranda, Ariel, Umbriel, Titania, and Oberon. The moon Miranda is particularly strange. It looks like it was smashed to pieces and then sloppily reassembled, with a jumbled up surface of cliffs, canyons, and different terrains all mashed together. Uranus is the only planet whose name comes from Greek mythology rather than Roman. Uranus was the Greek god of the sky. It was discovered in 1781 by an astronomer named William Herschel. He was a musician and composer who became a brilliant amateur astronomer. He built his own telescopes, which were among the best in the world at the time. When he first saw Uranus, he thought it was a comet or a star. But as he tracked it over several nights, he realized it was moving like a planet. It was the first planet to be discovered since antiquity. It doubled the known size of the solar system overnight. His sister, Caroline Herschel, was also a brilliant astronomer in her own right. She worked alongside her brother, discovered several comets herself, and was one of the first women to be paid for her scientific work. Together, the Herschels expanded our view of the cosmos. We have only visited Uranus once, very briefly. The Voyager 2 spacecraft flew past it in 1986. It gave us our only close-up images of this sideways, icy world. It remains a place of great mystery. Let's continue to the final planet in our grand tour, the eighth and farthest known planet from the Sun, Neptune. Neptune is the other ice giant. It is a near twin to Uranus in size and composition. It is also a deep, beautiful blue, but its blue is much more vivid and striking than Uranus's pale cyan. We're not entirely sure why Neptune is so much bluer. It may have something to do with an unknown component in its atmosphere. Neptune is the windiest planet in the solar system. Its winds are ferocious, reaching speeds of over 1,200 miles per hour or 2,000 kilometers per hour. That's faster than the speed of sound on Earth. These incredible winds whip the clouds around the planet, creating giant, dark storms. When Voyager 2 flew past in 1989, it saw a huge storm called the Great Dark Spot, similar in nature to Jupiter's Great Red Spot. This storm has since disappeared, and new ones have formed. It is a dynamic, ever-changing atmosphere. The story of Neptune's discovery is a triumph of science and mathematics. After Uranus was discovered, astronomers noticed that its orbit was a little bit wobbly. It wasn't moving exactly as the laws of gravity predicted it should. Some astronomers hypothesized that there must be another unknown planet even farther out, whose gravity was tugging on Uranus and causing these irregularities. Two mathematicians, one in England named John Couch-Adams and one in France named Urbain Le Verrier, independently set out to solve this incredibly difficult problem. They used only mathematics. They calculated where this hypothetical planet would have to be and how massive it would have to be to account for the wobbles in Uranus's orbit. Le Verrier sent his predictions to the Berlin Observatory. On the very first night they looked, the astronomers there pointed their telescope to the exact spot Le Verrier had indicated. And there it was. A new planet, Neptune. It was discovered with a pen and paper before it was ever seen through a telescope. It's one of the most beautiful stories in the history of science. A stunning confirmation of Newton's law of universal gravitation. Neptune has 14 known moons. The largest of these is Triton. Triton is a fascinating and strange moon. It orbits Neptune backwards in what's called a retrograde orbit. This suggests that Triton was not formed with Neptune. It was likely a dwarf planet, similar to Pluto, that wandered too close to Neptune and was captured by its gravity. Triton is one of the coldest objects in the solar system. Its surface is a frozen landscape of nitrogen ice. But it is not geologically dead. The Voyager 2 flyby revealed dark plumes erupting from its surface. These are not hot volcanoes like on Io. These are cryovolcanoes, or ice volcanoes. It's thought that sunlight warms the dark nitrogen ice just enough to cause it to turn into gas and erupt, carrying dark, dusty material with it. So even in this incredibly cold, distant place, there is geological activity. Our tour of the 8 planets is now complete. From the scorched rock of Mercury to the windswept ice of Neptune. But our journey is not over. The solar system does not end here. We are now entering a vast new realm, the third great zone of our solar system, the Kuiper Belt. Beyond the orbit of Neptune lies a region of space that is like a second, much larger asteroid belt. This is the Kuiper Belt. It is a donut-shaped ring of icy bodies. It's thought to be the source of most of the short-period comets, the ones that visit the inner solar system every few decades or centuries. The Kuiper Belt is vast. It starts at Neptune's orbit, around 30 times the Earth's distance from the Sun, and stretches out to about 50 times that distance. It is home to hundreds of thousands of icy objects larger than 60 miles across, and likely trillions of smaller ones. These are the pristine, frozen remnants from the formation of our solar system, the deep frozen leftovers. And the king of the Kuiper Belt is its most famous resident, Pluto. For 76 years, from its discovery in 1930 until 2006, Pluto was considered the ninth planet. It was the small, cold, distant outlier of the planetary family. Its discovery was another story of patient searching. After Neptune was found, some astronomers still saw small discrepancies in its orbit and thought there might be a planet X even farther out. An astronomer named Percival Lowell dedicated the last years of his life to searching for it at his observatory in Arizona. He died before he could find it, but the search continued, and in 1930, a young astronomer at the Lowell Observatory named Clyde Tombaugh finally found it. He spent countless hours painstakingly comparing photographic plates of the night sky, looking for a tiny point of light that moved from one night to the next. And he found it. A tiny, faint dot moving slowly against the background of stars. He had found Pluto. For decades, Pluto was just a fuzzy point of light, even in our best telescopes. We knew it was small. We knew it was icy. We knew it had a large moon named Charon, which is almost half its size. But we didn't know much else. That all changed in 2015, when NASA's New Horizons spacecraft flew past Pluto. It was an incredible 9.5-year journey across the entire solar system. And the images it sent back were breathtaking. They transformed Pluto from a fuzzy dot into a vibrant, complex world. We saw a world with vast, smooth plains of frozen nitrogen, right next to towering mountains of water ice. The most prominent feature is a huge heart-shaped glacier on its surface, informally named Tombaugh Regio. We saw evidence of flowing glaciers of nitrogen ice. We saw a thin, hazy atmosphere. We saw a world that was surprisingly geologically active. It was not the dead, frozen ice ball we might have expected. It was a dynamic and beautiful world. Now let's talk about Pluto's demotion. In 2006, the International Astronomical Union redefined what it means to be a planet. They came up with 3 criteria. A planet must orbit the sun. It must be massive enough for its own gravity to pull it into a round or nearly round shape. And it must have cleared its neighborhood of other objects. Pluto meets the first 2 criteria, but it fails the third. It is located in the crowded Kuiper Belt. It has not cleared its neighborhood, so it was reclassified as a dwarf planet. Many people were upset by this. They had grown up with 9 planets, but you can think of it in another way. Pluto was not demoted. It was promoted. It is no longer the smallest, weirdest planet. It is now the largest and most important member of a whole new class of objects. It is the king of the Kuiper Belt. And it is not alone. Since the 1990s, we have discovered many other large objects in the Kuiper Belt, other dwarf planets. There is Eris, which is actually slightly more massive than Pluto. Its discovery is what prompted the whole debate about the definition of a planet. There is Makemake. There is Haumea, which is a strange, elongated, football-shaped object that spins very rapidly. There are many others, with names like Quaoar, Sedna, and Orcus. The discovery of the Kuiper Belt and all these new worlds has fundamentally changed our understanding of the solar system. It is not just 8 planets and a few asteroids. It is a vast, rich, and populated place, with entire zones of objects we are just beginning to explore. Let us drift now beyond the Kuiper Belt. Our journey is nearing its final frontier. We are heading to the most distant, most mysterious, and most vast region of the solar system, the Oort cloud. The Kuiper Belt is a donut-shaped disk, but surrounding the entire solar system, like a giant, thick-walled bubble, is a theoretical region called the Oort cloud. It was first hypothesized by a Dutch astronomer named Jan Oort in 1950. The Oort cloud is a vast spherical shell of icy bodies. It is thought to be the home of the long-period comets. These are the comets that take thousands or even millions of years to orbit the sun. They come from all directions in the sky, not just the flat plane of the solar system. This is what suggests their home is a sphere, not a disk. The scale of the Oort cloud is almost impossible to comprehend. It is thought to start at perhaps a few thousand times the Earth-Sun distance and extend out to 50,000 or even 100,000 times that distance. That is about a quarter of the way to the next nearest star, Proxima Centauri. It is a truly enormous structure. The Voyager 1 spacecraft, the most distant human-made object, is traveling at over 38,000 miles per hour. It will not reach the inner edge of the Oort cloud for another 300 years, and it will take it about 30,000 years to cross it. The objects in the Oort cloud are the most distant, most loosely bound members of our solar system's family. They are barely held by the sun's gravity. Occasionally, the gravitational nudge of a passing star, or a giant molecular cloud, or the tides of the Milky Way galaxy itself can dislodge one of these icy bodies from its distant orbit. It can then begin a long, slow fall toward the inner solar system. And as it gets closer to the sun, the ice begins to heat up and turn into gas. This gas streams away from the object, creating a glowing cloud around it called a coma. The solar wind and the pressure of sunlight then push this gas and dust away, forming the beautiful long tails that we associate with comets. These dirty snowballs, as they are often called, are some of the most spectacular visitors to our night sky. They are time capsules from the very birth of the solar system. They have been in a deep freeze in the Oort cloud for billions of years, perfectly preserved. When they visit us, they give us a chance to study the raw materials from which everything in our solar system was made. Famous comets like Halley's Comet, which returns every 76 years, or Hale-Bopp, which was a spectacular sight in 1997, are messengers from this distant, invisible realm. They remind us of the true, vast scale of our solar system. And so, we have reached the edge. We have traveled from the fiery heart of the sun, past the rocky worlds, through the asteroid belt, past the gas and ice giants, to the Kuiper Belt, and out to the vast, cold, dark sphere of the Oort cloud. This is our home, our solar system, a place of incredible beauty, diversity, and mystery. But the prompt for our lecture tonight was the fascinating facts behind solar system and more. It's time for the and more. It's time to take one final giant leap. It's time to leave our solar system behind entirely. For thousands of years, we have looked up at the stars and wondered, are we alone? Is our sun the only star with planets? Or are there other worlds, other solar systems, scattered throughout the galaxy? It was a question that we could only speculate about. But in the last few decades, that has all changed. We now have the technology to find planets orbiting other stars. These are called exoplanets, and we have found thousands of them. How do we find a tiny, dark planet orbiting a bright, distant star? It's incredibly difficult. It's like trying to spot a firefly next to a giant searchlight from miles away. So astronomers have developed some very clever indirect methods. One of the most successful methods is called the transit method. Imagine you are looking at a distant streetlight. If a tiny moth flies in front of the light will dim by a very small amount for a brief moment. Astronomers use powerful telescopes, like the Kepler Space Telescope and now the TESS mission, to stare at hundreds of thousands of stars at once. They look for these tiny periodic dips in a star's brightness. If a star's light dims regularly, by the same amount and for the same duration, it's a very good sign that a planet is orbiting it and passing in front of it from our point of view. Another method is the radial velocity, or wobble method. A planet doesn't just orbit its star. The star and the planet both orbit their common center of mass. Because the star is so much more massive, it just wobbles a little bit. We can't see this wobble directly, but we can detect it in the star's light. As the star wobbles toward us, its light is slightly shifted to the blue end of the spectrum. As it wobbles away, its light is shifted to the red end. This is the Doppler effect. By measuring these tiny shifts, we can infer the presence of an unseen planet and even estimate its mass. Using these methods and others, we have unleashed a revolution in astronomy. We now know that planets are not rare. They are incredibly common. It seems that most stars in our galaxy have planets. There are likely billions, perhaps even trillions, of planets in the Milky Way alone. And the planets we are finding are wonderfully diverse. There are hot Jupiters, giant gas planets orbiting incredibly close to their stars, with years that are only a few days long. There are super-Earths, rocky planets that are larger than Earth, but smaller than Neptune. We don't have any of those in our own solar system. There are mini-Neptunes. There are planets that orbit two stars at once, like the fictional planet Tatooine from Star Wars. There are even rogue planets, wandering through the galaxy on their own, not tied to any star. We have found planetary systems that are very different from our own. Like the TRAPPIST-1 system, which is about 40 light-years away, it has at least 7 Earth-sized rocky planets, all orbiting a tiny, cool, red dwarf star. Several of these planets are in the star's habitable zone, where liquid water could potentially exist on their surface. The next great challenge is to study the atmospheres of these exoplanets. When a planet transits its star, a tiny amount of the star's light passes through the planet's atmosphere. By analyzing that light, we can look for the chemical fingerprints of gases, like water vapor, methane, oxygen, or ozone. These could be potential biosignatures, or signs of life. The James Webb Space Telescope is a powerful new tool that is doing exactly this. It is giving us our first real glimpse into the air of other worlds. We are living in the age of exoplanet discovery. We are the first generation of humans to know, for a fact, that our solar system is just one of many, that our Earth is just one world among countless others. And with that, our journey comes to a close. We have traveled from the familiar comfort of our own sun, out to the farthest, coldest reaches of our solar system, and then beyond, to the realm of other stars and other worlds. Let's take a final moment to reflect on this journey, to let the vastness and the wonder of it all settle into our minds as we drift off to sleep. The knowledge we have gained is astonishing, but it is not just a collection of facts and figures. It is a story about our origins, our place in the universe, and our connection to the cosmos. Every atom in your body, except for the hydrogen, was forged in the heart of a star that lived and died long before our sun was born. The carbon in your cells, the calcium in your bones, the iron in your blood, it is all stardust. We are, quite literally, made of the same stuff as the stars and the planets we have just visited. As the great scientist Carl Sagan famously said, we are a way for the cosmos to know itself. When you look up at the moon, remember that its steady presence has kept our planet stable and nurtured the conditions for life. When you feel the warmth of the sun on your skin, remember its long and patient journey to reach you. When you see a shooting star, remember the ancient asteroids and comets, the leftover building blocks of our world. This knowledge doesn't make us feel small. It makes us feel connected to a grand, ancient, and beautiful cosmic story. It fills us with a sense of wonder, a sense of awe, and a sense of peace. The universe is not a loud, chaotic place. Most of it is quiet. It is vast, silent, and patient. The planets spin in their orbits with a silent, graceful rhythm. The stars shine with a steady, peaceful light. The galaxies turn in a slow cosmic dance that takes hundreds of millions of years. As you lie here now, ready for sleep, feel yourself as part of that quiet, cosmic rhythm. Feel the gentle, slow spin of our own planet. Feel the pull of the sun's gravity holding us in its steady embrace. Feel your own quiet breath in and out. A small, personal rhythm that is part of a much larger one. The search for knowledge continues. There are still so many mysteries to solve. What is dark matter? What is dark energy? Is there life on Europa, or Enceladus, or on one of the trillions of exoplanets? The story is far from over, and that is a wonderful thing. It means there will always be more to discover, more to be amazed by. But for tonight, our journey is done. Let the vastness of space be a comfort. Let the quiet rhythm of the cosmos be a lullaby. And let the wonder of it all fill your dreams. Close your eyes, take a slow, deep breath, and drift peacefully into the quiet, starlit night. Sleep well.
you.